Hi, in part 1 of Contour Detection 101, we learned the basics, how to detect and draw the contours and do some other things. In part 2, we learned to do some manipulations with contours. In this part, we're going to learn one of the most important things regarding contours in OpenCV, and that is contour analysis. This is really important because by doing contour analysis, you will be able to detect and recognize objects. You can also create some interesting applications like real-time shape detection using the techniques that you're going to learn in this tutorial. So let's get started. So for this tutorial, we'll be using this Jupyter notebook. So make sure to download it from the link in the description below. All right, let's start. So first I'm gonna import all the required libraries. As you can see, I'm importing OpenCV, NumPy, Pandas, transformation module, which I just created. I'll later on get into what it does exactly, and matplotlib. And I think the math module too, yeah. So then I'm gonna read in the image using cv2.imread function, and then I'm gonna display it using matplotlib. All right, so let's run this cell. So this is the same example that we have been using in the past two tutorials. So after displaying this image, I'm gonna go ahead and convert it into grayscale. Since this is already a pre-processed version, it's gonna be converted into binary, and then I'm gonna pass it directly in the find contours function and then get the contours back. Then I'm gonna pass these contours in the draw contours function to draw out each individual contour, and then I'm gonna display this image with matplotlib. All right, so all these contours are drawn out. So let's get to the real business, which is contour analytics. And the first thing that we're going to see is image movements. Now, image movements are weighted averages of pixel intensities in the image. And these are really useful because by using image movements, you can find out useful things like the center of mass of a contour, or the centroid of the contour, or the area of the contour, things like that. And these properties are really useful to understand what the contour looks like, what the shape of the contour is, and properties like that. And this way you can differentiate between one contour and another one. And by doing that, you can recognize certain objects. So some of these properties are invariant to geometrical transformation like translation, rotation, scaling, and things like that. So we'll look into which property is invariant to what in a bit. So first of all, let's take a look at how we can use extract image movements of any contour. So for that, what you need to do is first select any individual contour. So from the list of contours, I'm going to extract a single contour. And I'm right now I'm extracting this contour, the biggest one, and then I'm going to pass this contour into the cv2.moments function, and then I'm going to get the moments back and store it in the variable called m, and I'm going to then print out this moments variable. So what this is going to give me, if I run this code, is a dictionary of all the image movements that are extracted from this contour. And to learn more about these movements, what you can do is take a look at this Wikipedia article that is linked here, which discusses how each image movement is calculated, and it goes into a lot of maths regarding how the contours work. The math is not that complicated in case you're interested in how contours are calculated. As you can see, all these the formula required for these contours, and some details regarding other things. So this is the most interesting section here: translation invariant movements, scale invariant movements, and rotation invariant movements. And we're going to look at these particular movements are called the hue movements, and we're going to discuss these movements in a bit. So this is a really interesting Wikipedia article that goes into a bit of maths regarding how contours, how image movements and hue movements work. Image movements are in turn divided into three parts: raw movements, center movements, and then normalized center movements, and then there are hue movements. So it's really interesting. I've also printed out, in fact included an interesting Learn OpenCV article here, which also discusses upon some of the things in image movements. It's an interesting read. All right. So now that we have briefly covered what image movements are, why they are useful, let's use them to find out some interesting properties like the centroid of the contour. So we can do that by this formula. What I am doing simply here is dividing one image movement with another one, and this particular moment is the area of the contour. So by doing this for M10, I can get the x coordinate of the centroid, and by doing the same thing with M01 contour, which is the other one, I can get the y coordinate of the centroid. And then I'm printing out these values. So let's run this code. So this xy point is the centroid of this contour. And I extracted this centroid by using image movements, these two particular values. Now what I'm going to do is, extract the centroid of all the contours in this image. So for that, I'm going to first make a copy and then iterate through all the detected contours. So for each contour, I'm going to extract its image movement, and then I'm going to extract its x and y coordinate for the contour. And then using these coordinates, I'm going to draw a circle around the center of each contour and then display the results. As you can see, a circle has been drawn on the center of each detected contour. And this is really useful in a lot of cases. A lot of times, maybe you need the centroid of the detected object in order to do something or do some manipulation around that. So really useful technique. Now the next thing we can do is find the area of contour. We already have a function which we learned in the previous tutorial called cv2.contourArea. Right, this gives us the area of any contour. You just pass in any individual contour and it returns to you the area. So let's print it out. So this is the area. Similarly, we have an image movement called M00, which also gives you the area of the contour. So let's run this code. So as you can see, both methods are returning the same area. And these two are the methods if you need the area of the contour. All right, let's take a look at some other properties of contours, and these properties are really interesting because some of these properties would be invariant to scaling, translation, and rotation, things like that. So for that, what I'm going to do is first read an example image and then display it, and then we're going to work on that example image for the rest of the tutorial, for the rest of the few examples. So first I'm going to read an image called sort.jpg, and I'm going to convert it into grayscale, and then I'm going to threshold it. And then I'm going to get this binary image and pass it into the contours function and extract its contours. And then I'm going to select the first contour that is detected. And this image only contains a single contour. So the first contour would be the only contour that is being detected on this image. Then I'm going to draw the contour out and then display the results. So this is the sort. You might have seen this example in the previous notebooks. So this is the sort, and I've drawn out an contour outline on this example. All right. Now what I'm going to do is create use some contour properties and show you how they are invariant to things like translation, rotation, and scaling. So for doing that, I have created a Python module inside, this directory, and you'll get the Python file. So the file is called the transformation.py, which contains a function called transform, and what it does is it actually, this function either translates or scales or rotates the image, and what you do is just pass in the image file and select display equals to true, which displays the result, and it then randomly translates or scales and rotates depending upon if you've set these variables to true or false. So the syntax for that is this, and this is how it looks like. So let me just run this cell, and as you can see here, by just running this single line of code, it has taken this sort image, which is the original image, and then modified it to something like this. So what it did is it applied a translation of -43 in x direction and +30 in y direction, and then it applied a rotation of angle 154, and then it resized or scaled the image by 89%, meaning it sort of reduced the original size. So right now what I've set it is that I'm modifying each image randomly. So if I run this again, there's going to be a different modification. So if I run it again, there's going to be a different modification. So it's randomly applying all these three transformations to this image. So if you don't know already, the scaling is something like resizing the image. Then rotation is like rotating the image. And then translation is like shifting the image here or there, things like that. So you just shift the object in the image to, in X or Y direction. So this is how these three basic geometric transformations, work. So now we're going to take a look at some image properties that are invariant to these things, which means that even if you translate or rotate an object, these properties will be remain same throughout. So this is really useful. So for example, consider this. So consider an example. I have, I have this remote, right? And if this remote was a singular color like black or maybe red or any other color, and then what I did is create a color segmentation, and then after color segmentation, I would probably have gotten a mask, a binary mask, giving me black in the background and white in my detected object. So this area would become white and all the rest of the background would become black, which is a binary image. And this is the image that I want to pass in the contour. But what if I calculate some properties when oriented the this object as like this, and then I rotate it like this, then the contour properties would probably change. For example, if I take this image and move it to the camera, the area of this contour will increase, and if I move it back, the area would decrease. Similarly, there are other properties that maybe if I pick this up object here and move it sideways, some properties would change. So and then if I rotate this like this, some other properties might change. For example, if I'm drawing a bounding box, right? So if I draw a bounding box, a box would be like this, it would be drawn like this. But if I oriented it like this, then the bounding box would take a lot of space. So let me just draw this out. So if I have an image which contains a segmented, like a rectangular object like this, and then if I wanted to draw a bounding box, like this is the object, and if I wanted to draw a bounding box around it, then it would be something like this, right? But if the same object, it's sort of rotated like this, right? The same, the object is rotated like this, then the bounding box around it would be something like this. The bounding box would be much bigger. So as you can see, as the contour, as the shape of the contour, as the orientation of the contour changes, some certain properties around that contour also change. And the best properties are those that are invariant to those changes. So, and these are the properties that we'll take a look at, because by analyzing these properties, we can differentiate and recognize a same contour in different orientations or translation or different scales. So this is really useful technique. So the first thing that we're going to see is the aspect ratio, and it's really simple. It's the ratio of width divided by height. And the thing about this ratio is that this property is invariant to translation. So even if I take this object that is detected as a contour, I move it around like this, this is gonna give me the same aspect ratio. So the width and height would remain the same, but aspect ratio won't be the same if I move this object closer or further from the camera, because then the width and height would not be remain the same, and this would cause problems. But this particular value is invariant to translation. So what you need to do is first draw a bounding box around the contour, like I just showed you, and then what you need to do is just divide the width by the height. You get the aspect ratio. And what I'm going to do is just print out the aspect ratio value, and then I'm going to transform this image and set translation equals to true. So it's going to randomly apply some translation to this sword image, and then I'm going to get the xy with height back with this modified contour, and then I'm going to display the second aspect ratio, and we're going to see that both aspect ratio would be the same. So what's happening here? I think I just yeah. So let me just run this. So as you can see, the aspect ratio initially was 0.994, and after the translation has been applied, the aspect ratio remained the same. So the aspect ratio property of a contour remained the same even after translation was done. So this property is translation invariant. Let's take a look at another property called extend. This is the ratio of contour area to the bounding rectangular area. So consider this. So if I have an image which contains a circular object which is detected as a contour, so the area of this circle is the contour area, and the bounding box area that is encloses this object is the rect area. And what extend is doing is it's dividing the contour area, meaning the circle's area with the rectangular area that's enclosing this contour. So it's dividing the circle area which is just width multiplied by height, which is the area of the rectangle, and then it's dividing contour area with this area. So it's really simple. And this property is invariant to, it's invariant to translation, and it's also invariant to scaling. So if I move this object, which is detected as a contour, closer and further from the camera, the extent would not change. The extent would remain the same. If I move it up and close, or if I move it sideways, the extent would remain the same. So this is an interesting property to use in order to analyze contour. So in order to calculate the extent, you can get the contour's area, you can extract the bounding rect, and then you can get the rectangular area by just multiplying with the height, and then you can get the final extent by using this formula by dividing the original area of the contour, which we got with contour area function, and with the rectangular area. So this is how you get the extent. I'm going to print out the extent before the modification, and then I'm going to print out the extent after the modification. And then we're going to analyze both of these values. As we can see, both these values remain the same even after a translation of 3844 was done and the image was scaled to 117% of its original size. So now let's take a look at another property called equivalent diameter. Now the definition for that is it is the diameter of a circle whose area is the same as the contour's area. So if I have a contour, something like this, then it has some area, right? And I can get that area by using contour area function like here. So what equivalent diameter mean is that draw a circle which should have an area equal to that contour's area, and then take the diameter of that circle. This is called the equivalent diameter. So this is the definition of equivalent diameter, and the formula for that is this. All you do is just take the area of the circle and then rearrange this equation so that it becomes this, and then you put this equation here. So what I'm doing is just putting this equation here, taking the square root of 4 multiplied by the modified area divided by the pi, and yeah, so it's really simple. And then I'm printing out the equivalent diameter before the modification, and then I'm printing out the equivalent diameter after the modification. And this particular property, it's invariant to translation, and it's also invariant to rotation. So if you translate or you rotate, equivalent diameter would remain the same, but aspect ratio and extent would not remain the same if you rotate the object. So this particular property is invariant to the rotation and the the translation. So if I run this, as you can see, the equivalent diameter is approximately the same before and after the modification, even if the rotation is done by an angle of 38 and translation is done like here. So these were the three interesting properties of contours that you can use to analyze contours. Now we're going to look at some more interesting and more robust properties called hue moments. But before that, let me just show you that how you can calculate the orientation of a contour. So for example, if I have a contour and which is rotated something like this, and you want to know what angle this contour is rotated at. So there are several techniques to do that. Let me first randomly transform a contour with some angle of rotation, and maybe just let me make that true. So yeah, I've rotated this angle by an angle of 115 degrees. All right, now I'm gonna get the angle. I'm gonna calculate what angle this modified contour is rotated at by fitting an ellipse on it. And then I'm gonna do the same thing again, but this time I'm gonna fit a rotated rectangle on it and then get the angle. So if I run this, I'm going to get an angle of 107.9 something like that, and then I'm going to get an angle of 118 point something like that. If I run this again, I'm going to see some changes. So this is 46.88, this is 45.0. So I've seen maybe some angular limit, these two are approximately same, but past a certain angle, these two vary a lot. So one thing that probably confuse you is why all the three angles are different. I have applied a rotation of 176 here, and the fitting ellipse is giving me 46 something, and the circle minimum area is giving me 45 something. So why are these angles a lot different? By the way, right now these two angles are approximately the same, but as we saw earlier, these two can be drastically different depending upon what the original angle is. So the thing is, what's happening here is that when I rotated this sword, what the geometrical transformation did is that it picked up the sword from the center and then rotated it from the center. But when I fit an ellipse around it, so what it's doing is that it's fitting a sort of an ellipse, and then the ellipse is making an angle to some reference point, and then it's calculating the angle for that ellipse from that reference point. The same thing is happening with this rotated rect. So that rotated rect is making some angle at some reference point, And from that reference point, the angle is returned to you. So if you're making a computer vision application, that depends upon how the target object is rotated, and you need to trigger some things regarding how the object is rotated. You need to figure out what are you going to fit on that contour. So you can fit a rotated rect, you can fit an ellipse, you can also fit a line. I've not covered a line because that the code for that is a little bit cryptic, but it's the same concept. You fit a line. So you do something like this, you draw a line and then you calculate some reference point. The reference point can be a horizontal line, and then you calculate the angle that the line is making at that reference point, and then you get the angle. So the thing is that you first need to calibrate what angle that your target object makes when you fit a particular object on it. And then note these angles down. So the next time the contour makes that angle, you trigger the events that you want. This doesn't have to do with analytics exactly, but this is a really useful technique which I've used in a couple of applications. So that's why I've covered it here. Now let's take a look at the final analytical technique that's called hue movements. And this is a really powerful technique. You can use hue movements to match different contours or differentiate between different contours, or recognize same contours in different orientations, translation or scales. So all you need to do is first use the function called cv.movements to get the movements, and then pass the movements in another function called cv2.hueMovements. That's it. And once you pass this movements in the hueMovements function, you get the hueMovements back. And then I'm just printing out the hueMovements. So these are the 7 hueMovements, and all these 7 are invariant to rotation, translation and scaling. So all these 7 properties are invariant to all those 3 basic transformations. Now let's take a look at the hueMovements. But before that, what I'm going to do is transform these values to log scale. This is in linear scale, and I'm going to transform it to log scale. The reason for doing that is that take a look at this. So these values are vary in different ranges. So for example, the first hueMovement, it's just exponent -1, and then the 7th hueMovement is exponent -11. So the range for each of these values is drastically different. So in order to get all these values in the same range, I'm gonna transform this into log scale so that it's comparable. So once I do that and then display it out, I'm going to see these results. As you can see, now the range is pretty similar. All these are in a similar range, all these 7 hue properties. Let me just run this code again. All right. So what I'm just doing is applying this line of math to convert this linear scale into a log scale. And then I'm using pandas to just display these movements. You can just print it out if you want, but I wanted the index to appear besides these actual values, so that's why I'm using pandas to display it. This is just optional. So after I've displayed it, I'm going to modify the contour. So I'm going to modify the sort contour. So let me just run this again so it's somewhat different. So yeah, this was the original image. Now the modified version looks like this. And in the modified version, I've applied a translation of -3148, an angle of 122, and image has been resized to 87% of its original size. So all these 3 transformations are done. Now let's take a look at the modified hueMovements. So I'm going to calculate the hueMovements again in this modified version, and then we're going to take a look at the difference between the original hueMovements and the modified hueMovements values. So as you can see, all these values are approximately the same. All these 7 properties are same regardless of the fact that I translated the image, I scaled the image, and I rotated the image. So this is something really powerful. So you can use these hueMovements in order to match shapes. And in fact, I'm going to teach you how you can build some exciting shape detection based applications on top of these things that you've learned today. And we're going to learn to do some other exciting things with contours, like how to determine the distance between an object and the camera, how to sort objects, and how to use the hierarchies properly, and a lot of other nitty-gritty details regarding contours. And then we're also going to learn a lot of other applications that can be built around contours in OpenCV. But all that would be covered in a separate course. The course will be called Building Contour Applications with OpenCV and Python. It's a really interesting course, and it's just a one-day course. So it's a mini course, and it would be released in a couple of weeks on Bleed AI. So stay tuned for that. And if you enjoyed this video, make sure to subscribe to this channel, and I'll see you in the next video. Bye.